All right, we are going to do for algebra based second semester chapters 20.2, section 2 through 20.3, section 3. This is lecture 2 on this chapter. In case you're wondering, we're going to talk about resistivity and resistance and how we can apply that to some situations. Now, you got to keep in mind, we can force electrons to go through any material, all right? You just have to have a high enough voltage potential, and you can make it happen. So it flows fairly easy, right, through conductors because there's little resistance. Conductors have all those extra free electrons, and they're happy to just let them go around and flow through. Insulators don't want that, right? Insulators, they try and keep that those electrons from flowing. So what we say is they have a high resistance. Okay, well, conductors have a low resistance. Everything has a resistance, right? All the mediums have a resistance. We just have some that are higher resistances than others, some materials. And it's a lot higher, okay? So it's very, very low resistance for some materials and very high resistance. Now, we're not going to talk about superconducting materials or whatever. We're going to leave that out of it for now. We all know the adage about the path of least resistance and that the electrons are going to want to flow through conductors, right, versus the higher resistance insulators. And, you know, that just kind of is intuitive, makes intuitive sense. So whatever the media or the medium the current needs to flow through, it has some resistivity. All right, and we're going to start talking about the difference between resistivity and resistance. Okay, so resistivity, in quotes here, that is a property of the material. Okay, and we give that a symbol of rho. Okay, so this is our resistivity. And, you know, rho is also density of a material, but when you're dealing with currents and all that stuff, you gotta just say, oh, well, now I know rho is the resistivity, okay? And it just quantifies the inability of electrons to move through the material, all right? And now, when we measure current, what are we measuring? We're not measuring the actual flow of the electrons, we're measuring the flow of the holes going in the other direction. Okay, keep that in mind, all right? Current is going in the opposite direction. Thank you very much, Benjamin Franklin. So we want to make objects that have a certain known resistance, okay? And we use, as an engineer of some system, you want to do that, right? You want to know what the resistance is. So we use materials with a certain resistivity, and then that we can shape, okay, those materials to give us a resistor of a known resistance. Okay, we want to be able to predict and know what that resistance is going to be. So what do? We choose a material with a certain rho, okay? And then we shape it. And most often, we shape it in a cylindrical shape. You guys have seen on your circuit boards, your resistor comes out of the board and it has some shape like this, and then it goes back into the board, and this is copper, right? And we don't know what this material is, some unknown material, but it's shaped like this, okay, with some radius and some area. So we can figure out what the area is, and we can measure the length of the material, right? So we know the length, we know the radius, and we know the resistivity because we chose the material based on its resistivity. And with these three properties, we can predict the resistance for the resistor. That's our whole goal. So the resistance, that resistance goes up as the length gets longer, okay? Can you see that? So if we make this longer, of course it's going to go up. Our resistance is going to go up. So that means it's proportional. Oh, that means our resistance is proportional to the length. And it'll go down as we make the area larger because it has more that it can flow through and we're not restricting its flow, right? It's just like allowing water to flow through a large sluice versus a very narrow straw, right? You can get water to do different things. And so the larger the area, the lower the resistance. So that leads us to this right here. I'll start using a different color. That leads us to this one right here. So we also, well, I mean, it's kind of obvious that if the resistivity of the material goes up, then our resistance is going to go up too. So those three things we have to keep in mind, and we're going to put those three things into an equation, and combining them gives us our resistance is equal to our rho times our length divided by our area. And then that allows us to predict, right? And we know what those things are. So there's a table in the book, 20.1, that gives you rho for many materials. And so if you have a question in the homework that requires you to look up a rho, that's where you're going to go. And resistance has units of ohms. Let's talk about units for a second. And that's a capital omega. So you can see why we want to call it why we want to use omega, because ohm rolls right off the tongue from omega. So that works. And we can rewrite the equation as in terms of rho, and we get this equation here, and instead of ohms, we get ohm meters because we're multiplying by area now and dividing out, so we end up with an extra meter in the situation. All right, so let's do an example. What is the diameter of the filament in a light bulb? Well, our filaments are made of tungsten. In our case, we're going to choose tungsten to do this. And come on now. So we've got tungsten, and we're given that the resistance is 0.35 ohms, and it's got a length of 4 centimeters long. So I'm just going to convert that length to meters. We always want to use SI units, so put it in terms of your SI units. So we've got our meters, and we want to know what the diameter of this thing is. Okay, so a diameter is 2 times the radius. So here's our equation, D equals 2 times R. So what are we going to do? We want to put it in terms of R so that we can substitute in into this R squared, this D over 2. And that's what we're going to do. So we did that. And we're going to solve. We want to solve for D. So 2 squared is 4. That's going to put a 4 up into the numerator on the other side. We're going to multiply by our rho times our length. And we're going to divide by the resistance and pi. All right. Pi finds its way into our equations. Just finds its way in there. Okay, so what does that mean? D is equal to 2, because we got to take the square root of both sides. Square root of 4 is 2. Then we're going to multiply on the inside of the square root rho L divided by our resistance times pi. All those numbers are nice and easy. We've got them, and so D is equal to 9.0 times 10 to the minus 5 meters. So it's a very thin little resistor, and it's roughly about the same size as the conductor that's leading to it. So if you look here, we've got copper coming in and going out, and then we've got the resistor in the middle of our omega, and then that thing is going to heat up, our tungsten in the middle, and that's going to heat up and give us some resistance in ohms. All right. So it turns out that resistance and resistivity get larger as the temperature goes up. Okay? So if that temperature, we know it's going to go up. So the resistance at the beginning, R naught at the very beginning, goes up to some R final. Okay? And there's an equation for that. And it depends on your material. All right? So every material has, if it's ohmic material, it's going to use this equation right here. Okay, and so we're talking about what the resistivity is, our final resistivity, as a function of the temperatures that change. Okay, so for most materials, this equation works, if we do a delta T around 100 Kelvin. But for tungsten, this thing works all the way up to 8,000. It works from 100K to 8,000K, and maybe even goes higher. Nobody cares, because if it gets hotter than 8,000 Kelvin, maybe 10,000 Kelvin, we don't really see it anymore. It goes ultraviolet, and we can't visually see it, so we don't care. We just want tungsten to light up our room, and we can only see certain photons, their energies, and those energies come from the temperatures of the material. So delta T is, of course, our change in temperature. Alpha we call the temperature coefficient of resistivity. All right? And our rho naught is the resistivity at T naught, and rho is the resistivity at T final. So this is usually the one that we want to figure out. Our rho final is usually the one that we want to figure out, or we don't know, right? We know a lot of the other stuff, but we don't know that. So we can do this another way, because what if we want to just deal with the resistor, not the resistivity? Well, we can rewrite rho as R is equal to our resistance times our area divided by the length. And if we insert that, we get this equation. So if you notice, we've got A over L on both sides. We've got our R naughts, and we've got our R final. And the A over L on both sides, these guys cancel out. And we're left with R is equal to R naught times 1 plus alpha over delta T. All of that works really well. So we can really just memorize one equation, and we can substitute in either our resistivity or our resistance. And we're golden. We're ready to go with that. So this leads us to Ohm's law. So let's talk about what's happening. If the electrons are moving, our electrons are moving to the right, then our current is to the left. Okay, so we can see this current I moving to the left. And if the temperature goes up, right, then our current is going to change. And we're going to talk about what's happening there. But before we get to that point, let's just talk straight about our current and our voltage and our resistance, okay? So we can see that if the voltage goes up, so we've got some voltage between A and B, and we can make that, it makes the charges want to move. So the current is going to go up if the voltage goes up, all right? But if the resistance goes up in the material, our current goes down as the resistance gets bigger. So that's an inverse relationship. We've got a direct proportionality here. And so Gregor Ohm used these facts, all right? And that's why we gave it the name ohms, because we're honoring him, right? Because he did this work. And he said, well, if we combine those two things, then our voltage is equal to, this is a better way to look at it, our resistance is equal to the voltage divided by the current, but you can rewrite that, okay? And it's most commonly seen as V equals IR, okay? Either way, however you want to write it, but that's how it works. And if R is equal to V over I, oh boy, excuse me, then we have 1 volt over 1 amp is equal to 1 ohm, okay? And it's very, very easy. Everyone's happy, nice and easy. But I can't tell you guys how much you're going to use this V equals IR. That's why I've got the 3 exclamation points. The ridiculousness of it, because really we're going to use it all the time. Okay, if you're not sure what to do in a problem, throw V equals IR at it and see what happens. Okay, so we're going to use that all the time. All right, let's do an example of this. So we've got a car. We've got a car with a 12-volt battery, like most cars do, and we've got a 2.5 amp circuit to a headlight, and the circuit kind of looks like this. So we've got our headlight here as a resistance. We've got current flowing through this thing, and we know that we've got some voltage for the battery. And we're gonna discount the EMF situation here. We're just gonna do our voltage. So all we have to do is what is the resistance of the headlight? We're going to figure that out. We've got our 12 volts. We're going to divide by our 2.5 amps, and that's going to give us our 4.8 ohms. So yes, we like this. It works well, and it's very easy to work with. So what happens? What is resistance? Well, it's resistance to flow. It doesn't want to flow, and it doesn't want to flow because it's heating up, right? So they just don't have clear paths as they're going. So they bump and they grind and they, work their way through the medium, and it's like a crowded highway. The side streets are faster sometimes because the highway is just jammed up. It's a mess out there. So you go on the side streets and you just work your way through town, trying to get from Broomfield down to the DTC. No, that would just be a slog. Forget it. All right. So all the rubbing is friction. Okay, and friction just heats up everything. All right, and it's a way for our system to get rid of energy through friction, and it leaves the system as infrared light. Okay, these photons come out of the system and they shoot off. Okay, so I'm pretty sure you guys have all had some electronics in your life where you've attached, you're starting to charge it up or whatever, and you notice when you touch either the rectifier or you touch some aspect, or maybe you're charging your phone and you touch it and you notice it's really hot. Well, it's hot because this is happening, right? We're forcing electrons through things, and friction is building up and it's just getting hot. If you find that you've got batteries that keep heating up and get hotter and hotter and hotter, well, you might want to get rid of them. It's time for new batteries. There's an energy loss, and our power is lost as a result. Okay, so not only do we lose energy, but we're going to lose power too. All right. Okay, so we'll talk more about power and energy later. But let's put all these things together and measure someone's temperature who's sick. All right, so we can do that with a digital thermometer, and this is what the inside circuit kind of looks like. You know, it's not perfect, but it's a good start. Now, if you haven't seen chapter 21 yet, that's fine, but batteries have some internal resistance. All right, all batteries have an internal resistance. They're not perfect. And so what my point here is that we, depending on how many times this battery's been used and all the stuff, we can't get a reliable voltage from that battery. All right, so we set up a circuit that uses a capacitor as our supply of voltage, and that works pretty well. Okay, so we're going to use this capacitor with a known voltage of the capacitance, from the capacitance. Okay, so let's look at this equation, and we're going to figure some things out. We're going to break this equation down and try and figure some things out so that we can go in and here's what we're going to do. We're going to put a little current measuring device right here. Okay, so we're going to measure our current flowing through the wire, and that's going to really help us figure out if you've got a fever or not, or if your baby has a fever, or your significant other or child, whatever. We are always, that's a worrisome thing. You don't want to have fevers, so we're going to do it. So the math is go through, you don't have to, but if you feel like you want to learn a little algebra, go through and take our equation. Let me take our equation and go from, come on, baby, come back to me. What is happening right now? Okay. All right. Go through and do a little algebra if you feel like you need to, and go through all these different steps. Okay. And we're going to go through and do this. We're going to solve these things, and we're going to notice that T naught is equal to 1 over alpha, and our T final is there. And we still have a little bit of math to do before we get done here, but we're going to stop with this equation right here. And we're going to start talking about what happens in our circuit. So the first thing we're going to do is close A. All right? So we're going to close this switch A. And what is that going to do? We're not going to close B yet. But what that's going to do is it's going to charge up our capacitor. Okay, so we want our voltage on our capacitor to get full. So we allow that to happen. The next thing we're going to do is open up A. Okay, we're going to open up A. And we're going to close B. And the thermometer needs to be positioned, of course, at this point. You're going to want to put it in your ear, your mouth, or wherever you're putting the thermometer. And we're going to take measurements of the current, okay, as this happens. So at first, we're going to have this, right? And usually that'll be like at room temperature, okay? So nice. So we figure out what that is. And after some time, we're going to measure, in the end, we're going to measure our final current. So we're going to go back to that equation I had circled earlier, and we're going to actually solve it. Again, a little bit more algebra, and we end up with this equation, which is really nice. So we know what the current is initially, and we're measuring the final current. We know what T naught is, and then that gives us our final temperature. So it's a pretty neat little system. And we just measure the current until it stops changing, right? We want to measure the current until it stops going up or down. Once it stops going up or down, that's our final T final. And we're done. All right, so let's do an example. A thermometer has 50 ohms. It's got a capacitance that'll supply a voltage of 3 volts. At room temperature, which we're going to say is 20 degrees Celsius, we've got this 293 Kelvin. And I'm actually going to use 293.15, and you'll see why in a minute. We need that extra little, we need the extra significant figures to get accurate, okay? We want to have we don't want to just say your baby has a weird, we want to know how accurate it is. We want to make it accurate. So we're going to use the 1.5. Okay. So the question is, what is the current I final if the thermometer reads a patient with a fever of 101.5? Okay, so that's that's about the breaking point between low grade and high grade. So we want to know what's happening. So we got to convert our Fahrenheit to Celsius, and then we're going to convert that to Kelvin. So this is the equation to convert from Fahrenheit to Celsius. We're going to do that, and 101.5 minus 32 is going to give us our 69.5. We're going to multiply that by 5/9, and that's going to give us our Celsius degrees of 38.6. You guys know how to convert. We're going to add our 273.15. I wrote 293, but I really wanted to write 273. 273.15 is equal to 0 degrees Celsius. So we're going to use that and convert our 38.6 degrees Celsius to Kelvin. And this is what we get. So that's our T final in Kelvin. Now we know what T final is. We know what our T initial is. We know what our initial current is, but we really want to find this. So we rewrite that equation as I final is equal to T naught over T final divided by, or multiplied by I naught. So we do that and we plug in the numbers. It's pretty simple. and we're left with a final current of 56.42 milliamps. And our current goes up, which means our current goes down, which means our resistance had to go up. And it did. And that all works out. So here's another example. We've got a tungsten piece of material. It has a very large range where this works. Okay, so a lot of things aren't as good as tungsten. Tungsten works well with this equation, and it's one of the things that we use the most in our filaments in the old days before we had good high efficiency light bulbs or higher efficiency light bulbs. So what are those numbers? So for tungsten, we've got this. We're starting out at 20 degrees C, which is 293.15, and our initial resistance is this. The question is, what is the resistance of the resistor at this temperature? Now, why do we care about this temperature? I don't know if you guys have gone to Lowe's or Home Depot or whatever trying to buy light bulbs, or Amazon. But what you do is when you're looking for really bright light or fairly bright light, white light, it gets whiter. So it starts off as a nice, warm, soft light, and everybody uses about a temperature of 3,000 degrees for that. And then 5,000 degrees makes it a little bit whiter, a little bit less warm. It's not so soft anymore. Kind of brightens up the room. This is mid-level. This is where people during the day, this is kind of a nice sunlight thing. And then there are offices and whatnot with those really, really bright blue-white lights where you got to just be able to see everything. It's stark. That's at 8,000 degrees Kelvin. I shouldn't say degrees Kelvin. Gosh, what am I doing? 3,000 Kelvin, 5,000 Kelvin, and 8,000 Kelvin. All right. So we don't care. We want to get up to 3,000 Kelvin. So that's our final temperature. So we're going to figure out our delta T. Well, that's 2707 if we take 3,000 minus 293. We're going to plug those numbers in to our equation. So here's our R naught, here's our 1, here's our alpha, here's our delta T. We're going to plug all that in, and we get our resistance. In the end, our final resistance is 4.61 ohms. So that's quite a difference, right? From our initial of 0.35 ohms, that's where we started out. And now our tungsten has heated up quite a bit, and it has this 4.61 ohms. Okay, lecture 2, down. All you guys got to do is watch a couple more and we're good.